So I figured I'd make a video talking about Virga and radar, and as I'm letting this loop, this actually does become pretty easy to identify with a little bit of practice. So obviously Virga, it's just precipitation evaporating or sublimating before reaching the ground. I guess evaporating if it's liquid, sublimating if it's solid. And it's, like I said, pretty easy to identify on a radar image. The key is to make sure you're using a PPI, so don't be using a CAPI or anything like that. So let's explore this case here. So this is just March 3rd, 2023. This is a snowfall in southern Ontario. And we're looking at Exeter radar here. On the left and right, I have reflectivity. On the left, it's tilt 1 or 0.4 degrees. So that's our lowest tilt. And on the right, I have tilt 4. Unfortunately, RadarScope only gives us the lowest 4 tilts. And that beam elevation angle is 1.6 degrees. Now you notice as this system is sort of moving in from the south, you kind of get this circular shape, higher tilts and lower tilts. That circular shape is a very telltale sign of Virga, and generally speaking, the higher the tilt is, the more likely you are to get kind of a perfect circle around the radar site. And again, that's the telltale sign of Virga. Essentially, as a general rule, anytime you have some sort of circular shape or distortion on a PPI radar image, you're probably saying something about that height above ground. So, in the case of a bright band, you're talking about your freezing level, maybe an above freezing layer. Maybe I'll make a video on those. In the case of Virga, that's where your precipitation is either evaporating or sublimating, is where that circle is, right? So, if we zoom in, and maybe I'll pause this. Now, usually at a higher tilt, you kind of get a perfect circle around the radar, but in this case, you kind of notice we don't really have this perfect circle around the radar. It looks like the southern side of the circle is closer than, say, the northern side of the circle. And I'm looking at the higher tilt here. Now, you notice north of the radar, there's not even any echoes at the lowest tilt, right? So that's kind of an easy giveaway for Virga right there. We have these echoes at higher levels, indicated here. RadarScope suggests 3.6 kilometer beam height. The lower tilt is probably closer to 1.4 kilometers. The higher one has echoes, the lower one does not. So somewhere between 1.4 and 3.6 kilometers, we have precipitation evaporating or sublimating. And what we can infer from that in real time is there's some layer of dry air, at that level. We don't necessarily know if the temperature dew point depression is 10 degrees or 50 degrees or what, but we probably have a pretty good idea it's not, 2, 3, 1 degrees, right? Otherwise that precipitation would probably be making it to the ground, wouldn't be turning into Virga. And so, in this case, it's not a perfect circle, like I said. It's closer to the radar, south of the radar, as opposed to north. The reason for that, as we saw, is this stuff is coming in from the south. So as it comes in from the south, it starts snowing at those higher altitudes here before it starts snowing at the higher altitudes north of the radar. So south of the radar has actually had more time saturating that dry layer as snowflakes sublimate into it and add water vapor, and that temperature and dew point converge on the wet bulb temperature. That's been happening longer south of the radar compared to north of the radar. So why is it closer to the radar south than north? Well, again, this is a PPI image, right? We know PPIs increase with height further away from the radar. So basically what's happening here is it's saturated down closer to the surface, south of the radar, as opposed to north of the radar. And again, that's because it's been snowing for a longer time, precipitating into a dry layer, adding moisture, converging on that wet bulb temperature, and eventually it should reach the surface, right? And basically, we go from this Virga circle. When that circle or donut hill fills in, right there for example, that's generally when you would expect this, I guess in this case, snow or precipitation to reach the surface. Now you notice as this circle closed on the upper level, the one closest to ground really showed this, heavier echoes move over the radar as well, right? Now London Airport is not super far from Exeter. It's just over here, kind of northeast of London. We can take a look at their METARs. So as we see, we had overcast skies much of the day, but notice in the afternoon how the ceiling starts to come down, and they start calling Virga at 20Z actually, and that ceiling keeps coming down, and the temperature and dew point, they're not super far apart in this case. Sometimes it's very dramatic, but not so much in this case. It's 1 over -3 at some point in the afternoon, 1 over -2. Ceiling starts coming down, and by 2141 they've actually got snow reaching the surface. It's 0 over -2, not a huge difference. And then not long after that it fully saturates, and this was a pretty good system, so 2141 we go to 4 miles in light snow, and this is what, 20 minutes later, 23 minutes later, we're half mile in snow, vertical visibility 500 feet. So a pretty dramatic change of events there. And I mean, looking at the radar, anytime you see yellow, yellow snow, beware of the yellow snow, right? So I figured I'd show another example, and for this one, I'm going to use Buffalo just so we can show, using GR2, some of the higher tilts on radar where you get that really nice circle shape. So I mean, if you're using GR2 or Nino for that matter, any software that's going to give you those higher tilts, you can, well, this will kind of show what you can see. So if we look at Buffalo, I think in this one, the transition from Virga to surface precipitation happened around 0Z, which is kind of nice because we had a balloon launch, so I figured I'd start by showing that. So here's the observed balloon. Of course, the 0Z balloons probably launched closer to 2315 or 2330Z. Point being here is those low levels are pretty dry, right? I think at the surface there it's like -1 over -15 or so, and it's even drier just above that at say 925. But then above that you have a pretty good layer of cloud, so it's plausible that there's snowflakes falling, and even in this sounding here. And so let's take a look at what the radar looked like at that time. So you can see south of Buffalo, we have this ground clutter here. That's just the higher terrain south of Buffalo. You also notice, if you're kind of a radar geek, this is volume coverage pattern 35, which is an extra sensitive one they like to use for winter setups. So this terrain is really standing out, but of course with the dual pole, it's relatively easy now to kind of quote-unquote filter that out by just using correlation coefficients. So I've got base reflectivity, correlation coefficient side by side here. And if we go through a few images here, we can kind of see, snow moving in from the south. And as it gets kind of around Buffalo, you notice how it kind of looks kind of solid to the south, but kind of patchy to the east or north or west. So that, on a low level PPI, this is kind of a telltale sign that we might have some Virga issues. But the thing I really wanted to show here was the higher tilt, so why don't we do that? So here's our lowest tilt, and as we go higher and higher, we see that circular shape. I mean, even at these lower tilts, when you see like a semicircle like this, that's still a Virga sign, right? Anything circular. And then we get the really nice full circle at our high tilts here. So here we're at 6.5 degrees, and I can zoom in. And the nice thing here is, because we're at such a steep angle, the radar never actually scans directly above, but because we're at a steep angle, you are kind of getting closer to looking straight above. So you see here, there's the radar sight, And what we're seeing here is the echoes seem to kind of disappear around 7,000 feet or so. Right? As we go forward with time, you notice even though they're weak echoes, they do eventually make their way closer to the radar. And again, we're looking at a PPI, so if something gets closer to the radar, we can also infer it's getting lower in height. And, you know, eventually here we get some blues right to the radar, basically, right? So that's probably a good sign that the snow eventually made its way down. And if we take a look at the obs from Buffalo, looks like, you know, again, very dry to start, -1 over -17. And then a 10-mile light snow, so a few flakes start making it through just before 1Z. And that's kind of what we're seeing here, right? 005Z, or 50Z rather. And of course, you know, later on, this would eventually become that kind of epic snow band that went through southern Ontario. So there you go, Virga. Notice it a lot in the winter with snow, and I seem to notice it a lot in the summer, mostly in the summer I would say under anvils, with, you know, downwind of anvils from thunderstorms. And anecdotally, I feel like it's maybe a bit more common in the winter with snow. But anyway, there you go.